This video is the normal distribution part 2. Now in this lecture, we assume that you have a basic knowledge of the normal distribution from part 1 and understand how to read and find areas from the graph. What we're going to do now is look at various application problems that use the normal distribution and how to calculate probabilities from the normal distribution. Now, suppose we have these two ladies, Whitney and Krishna, that own a business that produce a certain type of light bulb. The lifetime of these light bulbs are normally distributed with a mean 200 hours and a standard deviation of 40 hours. So the process tells us it's normally distributed, and we have the mean and standard deviation, which will be provided for you in each problem. We won't have to calculate that. First question asks, part A, find the probability that a bulb selected at random lasts more than 250 hours. All right, so this is where we need a basic skill of reading common phrases and interpreting them to the proper inequality symbol. So more than is definitely greater than. Now, as we learned from part 1 with the normal distribution, unlike discrete distributions such as the binomial, it really makes no difference mathematically whether we have greater than or equal to. But more than is greater than. So I am using the proper symbol here. So this distribution is not the standard normal distribution because remember the standard normal distribution has mean 0 and standard deviation 1. But we talked about how to convert from normal to standard normal. We'll take the mean, the value x minus the mean, divided by the standard deviation. So we're trying to get this into z, so we can either use the normal distribution table, or if you have the special type of TI calculator, you can use the normal CDF function. So let's see. So I'm converting my value of 250 to a z. 250 minus 200 divided by 40 is 1.25. If your answer doesn't divide evenly like this one is exactly 1.25, you would round this to 2 decimal places to use the chart. And even for the calculator purposes, to make your answer similar to what the chart answer would be. So we learned last time that we can do the greater than. I sketched a little picture here where the blue values represent random variable x with a mean in the middle, then 250, greater than 250, and then right below it are the converted z values. So the 0 is always in the middle for the z, and 1.25, so it's the area to the right of 1.25 on the standard normal curve. Now there's two ways we can do this. You can greater than, you can look up 1.25 and calculate 1 minus that value, or change it to less than and then change the sign of your z. If it's positive, make it negative. If it's negative, make it positive. I prefer this way so I don't have to bother with the 1 minus, but if you like the 1 minus better, that will be fine. So we go to the z chart and look this up. I'll look up this one. I may not look up too many z's in this section since we've kind of done this before, but here we go. Let's take a look at this one though, since this is our first one. 1.2 row, 0.05 column. There it is, 8944. That's the 1.25. So you would take 1 minus that if you're doing it that way. Otherwise, if you're just looking at the chart directly, by flipping it over, you don't have to take 1 minus that number. And something happened to my normal negative values on here. I don't know what happened. I'll open the file up again and see if I can get this to work. Some reason the negatives were not being displayed. Here we go. Negative 1.25, there it is. 0.1056. So by changing it over to the opposite sign, we got the answer directly. And it's 0.1056, or as a percent, it is 10.56%. I like to sometimes show the probability and the percent, because sometimes the question may ask for it as a percent, but you can see all you have to do is just use standard conversion to percent. And the calculator, normal CDF, I put a greater than, means you put the first number, the number first, 1.25, and then greater than means your second number will be positive 100, which we learned last time in the part 1, that represents positive infinity. Now, same data set. The next question says, find the probability that the bulb selected at random would last between 180 and 210 hours. So this is the proper way to write the inequalities from whenever you're between. That's saying that notation means it's greater than 180 and it's less than 210 at the same time. So we need to convert both of these to z's. So once again, from the original problem, the mean is 200. The standard deviation is 40. So 180 minus 200 divided by 40 at the low end. 210 minus 200 divided by 40 at the upper end. Once again, I got a little graph sketched here in terms of x and in terms of z. So the first z value is negative 0.5, and the second z value is 0.25, which I have written right below. So that's kind of the area where we want to find here. Now, also from part 1, we learned that when it's between two values, you find the z value of the larger number, and you subtract the z value of the smaller number. Keeping in mind, that your answer has got to be positive. It's a probability. So if you got the two area numbers, chart numbers reversed and subtracted and got a negative, it would just be the positive of that. Remember, z's can be negative, but probabilities and areas must be positive. So if you look up 0.25 on the chart, it's 5987. Then I'll go ahead and look up negative 0.50. Whenever the second number is a 0, the first column is your 0. So negative 0.5, and then that's the 0, 0 column. So that's a value of 0.3085. So there's that. So 5987 minus 0.3085 gives us 0.2902. So roughly speaking, we have an approximately 29% chance that we would pull a light bulb out at random and it lasted between 180 and 210 hours. That's what we just calculated. All right, let's move down to this next application. A Ford Focus manual transmission gets an average of 24 miles per gallon in the city with a standard deviation of 1.6 miles per gallon. What is the probability that a Focus selected at random gets more than 28 miles per gallon? Assume the mileage is normally distributed. So they kind of have to put something in there that it relates to the normal distribution, or it would be wrong for us to use the normal distribution calculations. So I wrote down the mean and standard deviation, 24 and 1.6. Now I need to write the problem statement. What is it asking us? All right, more than 28. That's not too tricky. Straightforward. More than 28 means it's the probability that x is greater than 28. So we have to convert to z by using the x minus mu over sigma formula. So 28 minus the mean 24 divided by the standard deviation of 1.6. And that turns out exactly 2.5. So I'll put a little sketch over here. So there's your area to the right, 2.5. You can use the 1 minus. I chose to flip the arrow and change the sign. I made it less than because our chart is based on less than. So by making it less than and changing the positive to the negative, I can look up negative 2.5 in the 0 column on the chart, and I would get 0.0062. And see the normal CDF, 2.5, 100, 0.0062. So that means we have essentially a slightly less than 1% chance that we would pull out a focus at random that gets more than 28 miles per gallon. That would be kind of a rare instance. So let's look at this next example. The monthly utility bills for a certain city in April are normally distributed with a mean of 100 and standard deviation 12. A utility bill is randomly selected. So we're going to pull one out and see what kind of question we're going to have here. Find the probability that the bill is less than $80. So here's my probability statement. Probability that X is less than 80. That's pretty straightforward wording, I believe. So I have to convert that to a Z. So it's 80 minus 100 divided by 12. Now, I'll show you we had to use rounding here because 80 minus 100 is negative 20 divided by 12. Negative 1.6666. So we round that to 2 decimal places. So I'm using negative 1.67. Now, since our problem is less than, oftentimes students, they're so set on that greater than, wanting to flip things around. When the problem is less than, that it's already in the form that the chart is displaying. So less than, don't do anything to it. Less than negative 1.67 means you just look up negative 1.67 and don't change anything. Let's see if I can fit negative 1 point. It'll be the 8th column because you're starting at 0, 0. Shrink this down just a bit. Negative 1.67 is right here. 0.0475. 0.0475. And there's the calculator, normal CDF. The next normal CDF is for the next problem. So negative 100, because you're starting from negative infinity, because you stay with less than. Negative 100, comma, to negative 1.67. And there it is. 0.47, rounded would be 0.475. Find the probability that the bill is between $90 and $120. Okay, the between's pretty straightforward writing here. 90 less than X, less than 120. I have to convert both of those to Z's. So it's 90 minus 100 divided by 12. 120 minus 100 divided by 12. Negative 10 divided by 12, rounded, will be negative 0.83. 20 divided by 12 is positive 1.67. So once again, when it's between two values, I look up the larger value, in this case 1.67 on the chart, and I'll get 0.9525. I look up the smaller value, negative 0.83, and that would be 0.2033. So I subtract the 2 and I get 0.7492. Roughly about a 75% chance that our bill would be between 90 and 120. And the calculator box has that one displayed, and there it is. There's around to 7493. But that's close enough. That's good enough. Same data set. Find the probability that the bill is more than $140. More than, greater than, convert that to a Z. 140 minus 100 divided by 12. 3.33. Greater than. I like the flipping it over whenever it's greater than. You might prefer the 1 minus. Flip the arrow over to less than. Change the sign of this number. Take the opposite of whatever it is. So positive 3.33 becomes negative 3.33. I look up negative 3.33. And it's going to be a very, very tiny number there. 0.0004. So we have a very small probability that if we select a bill at random, it will be more than $140. And one more here. Let me stretch that out. So find the probability that the bill is more than $85. All right, greater than. So we take 85 minus 100 divided by 12. This is our first one I did this on purpose so we would have greater than a negative. The other greater thans have been greater than a positive. This one's greater than a negative. So I want you to see that oftentimes students will, if you get used to the positive, they'll say, oh, okay, just flip it over and make it a negative when you're doing the greater than. Well, if it's positive, yes, you flip it over and make it negative. But this one's negative, so when the arrow flips from greater than to less than, it becomes positive. It's always becoming the opposite sign of whatever it was. So you look up positive 1.25, you will get 0.8944. And let's see. Let's look at my calculator box here. Now, don't let that e to the negative whatever, don't let that give you a hard time. That's just scientific notation, that e in the calculator box. We don't have to worry about that. It just means you take your, same thing saying like 10 to the negative 4 power, meaning you would just move your decimal 4 to the left, and that means there'd be 3 zeros in front of it. So this number right here, so that's the same thing then. That 4.34 blah, 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 10 to the negative 4 is 3 zeros in front of that number. So we're okay there. All right. And then the one we just did, negative 1.25 comma 100, 0.89435, which would round to 8944. All right, so let's move down to the next one. Make that a little darker here. I'm going to erase this one and work it out. Get rid of my picture here. The average time a subscriber spends reading the local newspaper is 49 minutes. Assume the standard deviation is 16 minutes and that the times are normally distributed. What is the probability that the subscriber will spend at least 60 minutes reading the paper? Okay, I'm going to write this out. I'm going to use proper notation here for at least, which is greater than or equal to. But mathematically, it won't matter. It's the same as this. For a normal distribution, not a discrete. So now I have to convert that 60 to a z. So I'll say probability that z is greater than 60 minus 49 divided by 12. All right, I'm going to not do the numerator in my head like I did for that other example I just cleared, but I want to show you something. 60 minus, you have to use parentheses here if you're going to do this in one step. Because if you don't, it's going to think the calculator is going to interpret that as 60 minus only 49 over 12. But all in one step, we're going to round that to 2 decimal places, and we're going to call that 0.92. Oh, looks like I just saw a mistake I made here. I'm sorry. You should be dividing by 16. I don't know where I got 12 from. All right, easily fixed here. 16, 0.6875, which I'll round that to 0.69. Actually, I'm going to write that in the next line. Greater than 0.69. All right, greater than, I'm going to use symmetry. In other words, I'm going to flip it over and make it negative 0.69. Now I'm going to draw it here real quick, just a quick 0.69. Now these drawings aren't mandatory, but they can be helpful. For example, if you sketch this, and let's say you look up positive 0.69 and you think that's the answer. Well, the picture right there tells me that that's less than half the graph. So even though I may not have put the 0.69, correct, it's to the right of 0 is the important thing, which means it's less than half, because 0, the total area is 1, remember? So 0 splits it into half. So left of 0 is 0.5, right of 0 is 0.5. So this has to be, so if I look up positive 0.69, I'm going to get a number larger than 0.5. So that picture tells me that there's no way that that's right then, obviously. 0.69 would be 7549. Well, that's definitely not 75% of my graph. So I flip it over, made it negative, and that's going to be the answer, negative 0.69. There it is, 2451. Yeah, so the shading little graph there, that's optional, but I certainly don't think it's a bad thing to do. So we're going to say 0.2451, which I had already indicated up there as the answer. There we go. Okay, let's see what we have here. The next example, suppose SAT math scores are normally distributed with a mean of 518 and a standard deviation of 115. So I wrote down my mean and standard deviation, and the first question I'll ask is, what percent, and I put parentheses probability, just to let you know. It wouldn't have to say probability in the question, but this goes back, you've seen me do problems here where I've written the decimal answer, written the decimal, and then wrote what the percentage was after it. So that's the same thing. So if it asks for percent, you just calculate the probability and then just convert it to a percentage. It'll be the same idea. So what percent of the scores would we expect to be less than 500? Which is the same thing as the probability of one score being less than 500. So we take x less than 500, convert it to z. 500 minus 518 divided by 115. And that doesn't divide evenly, but it rounds to negative 0.16. So it's less than. So less than means I can just look up negative 0.16 and I'm good. I don't have to flip anything. Now be careful that we pick negative 0.1, not negative 1.0. I see that mistake every once in a while. So it's negative 0.1. I go to the 0.06 column. It should be right there. 4364. So the probability is 0.4364, which as a percent would be 43.64%. So I wrote out to the side here that just means that we would expect about 43.64% of all scores to be less than 500. Now the next question is a new type of question. Interesting. If 1,500 SAT math scores were randomly selected, about how many of these scores would you expect to be less than 500? Now, early on in the course, we did some things with the relative frequencies and percentages, and we did some problems involving pie charts broken down into their percentages. And let's say you were given a grand total. Suppose you had whatever, 5,000 people, and whatever category they fell into percent-wise, and let's say that was 22%. How many people then would you have expected to fall in that category? And all we had to do was multiply the percent. So the case I just said was 22% times 5,000, which I believe is 1,100. So you would have expected 1,100 people then out of there would have been in that group. And that's what it would have been. So that, and the same thing applies here. All you do is multiply your percent of people that you expect in that group times the total number of people, and that would tell you how many people fall into that category. Now, oftentimes it won't be exact, so we would round just to the nearest integer, normal rounding here. So it's really not that complicated. I even wrote as a little equation here, like you're saying, X people out of 1,500 equals 0.4364. But all you do is multiply, now when I say percentage though, you multiply it, of course, as a decimal. So you multiply 0.4364 times your total. That's it. Round it. You see I got 654.6. Well, this obviously has to be an integer number because it's the number of people. So we would say 655 people we would expect to be less than 500. So that's not too bad. Just multiply the probability times the grand total. And here's something I threw in here. Sometimes you can get z-values that are not on your chart. I try to avoid this on exams, but we may have some problems that come up where this happens, so it's good to know. Really, once you get beyond, 3, 4 on the negative side, this chart goes to 0.002. I wish it went to 0.001, but, frankly, you can kind of use 0 in a way, and we'd be okay, or you don't need to use like 0.000 without 20 zeros after it. So you would just expect a very, very small answer. So the 0.002 is okay, a 0.0001, or even really approximately 0 is good enough for less than negative 6.5. And the other end of the scale, less than positive 6.5, the highest value in this chart's 9998. Most would say 9999. Once again, approximately 1. So don't let that cause you too much stress there. If you see my z-value is not on the chart, it's okay. So it's a low end of the chart, just use 0. High end of the chart, use 1. So I can have that explained right down here in words. And I just did a couple of calculations. You look at that, the first one for negative 6.5, 4.036 times 10 to the negative 11, which means you would have a decimal with 10 zeros in front of it. So I think you can kind of say close enough to 0. That'll work. It's not exactly 0. This other one's really not exactly 1 either, but it must be so close to 1 that it won't display it in scientific notation. So it's mathematically not exactly 1, but it's very, very close. Let's take a look at this example. Stanford Binet IQ test scores are normally distributed with a mean 100 and standard deviation 16. Find the probability that an IQ score selected at random is greater than 87. Greater than 87. So there's my probability statement, x greater than 87. So I take 87 minus my mean of 100 divided by 16. That rounds to negative 0.81 when you divide it. So it's negative 13 over 16 rounds to negative 0.81. I'm going to flip it over, change the sign. So I'm changing it to less than, which then makes it positive 0.81. Opposite sign. So you can look up 0.81 on the chart. And let's see what we have. 0.81, there it is. 7910. 0.7910, or as a percent, 79.1%. We would expect that many scores to be greater than 87. Now, part B. Suppose 500 scores are selected. About how many would you expect to be greater than 87? Just like the last problem. We take our percent and we multiply it, our decimal, and multiply it by the grand total. So we take the 0.7910 that we found for the probability, multiply it by 500, and we'd round that. You see in the calculator it's 395.5. So we would round that to 396, and we would expect about 396 out of 500 to be greater than 87. And the next question, which is the last question. Find the probability that an IQ score selected at random is between 85 and 95. Okay, between, we've already seen before, real straightforward. 85 less than X, less than 95. 85 minus 100 divided by 16. 95 minus 100 divided by 16. Should calculate to negative 0.94 for the lower end, negative 0.31 on the upper end. So I look up, as I wrote down here below, chart value at negative 0.31 minus chart value at negative 0.94. Remember, you got to get larger minus smaller because the final answer for this has to be positive. So negative 0.31 has a chart value of 0.3783. Negative 0.94 has a chart value of 0.1736. Subtract the larger minus the smaller, you get 0.2047. And there it is in the calculator. You just put the lower number, you put the upper number, and there it is. So you would expect about 20.47% of the scores to be between 85 and 95. And that concludes the normal distribution part 2.